because we got a little bit of time. So what is organic chemistry? Well, officially, it's the study of carbon compounds. There's some gray area there because you'll sometimes get people arguing about carbon monoxide or carbon dioxide, sometimes methane, but methane typically is classified as organic. Right? All of those contain carbon. Why might not they all be called organic? A lot of it kind of has to do with the origin of where it's coming from. Organic chemistry is largely driven off of biological molecules. So it's the study of all of the molecules that allowed us to study biochemistry. Okay? But now we manipulate those. We try and do something to them or make them do something else. Okay? So it's really getting the nitty-gritty details of studying in that. Okay? Which kind of sets us up for the very next class in the sequence. The next class in your sequence would be biochemistry. Okay, well, what's the point of biochemistry? Well, it's taking all of the tools you've learned in organic chemistry and now applying them to the very specific circumstance of biology. Right? In that application, that can make biochemistry a lot easier. It can also make it more interesting. Okay? Most biochemists you'll find, at least in my experience, if you quiz them like, hey, you're a biochemist, you studied biology and all that chemistry stuff. How did you like o-chem? Guess what the response is? Worst class ever. Totally didn't understand it. It was useless. I didn't learn anything. Your entire field is based on it. There's some logical leaps that kind of happen there. And that's because when we shift into biochemistry, we can kind of skirt chemistry for a little bit and we can move into the biology realm and we can deal with a lot more memorization and application of those larger facts instead of looking at structural things. Okay? I would love to say that that's a horrible thing to do. It's not. It's a different thing to do. Okay? So when I rip on biologists, I apologize if any of you are in here. Okay? What I'm ripping on is the fact that I don't like thinking that way. That doesn't make it wrong. Kind of, sort of? Okay. So, what is carbon? I saw a couple of people furtively look at the periodic table like, don't look, I didn't do it. You can do whatever you want, within reason. Looking at the periodic table is within reason. Why would you look at the periodic table? Carbon's on there, okay. What does it tell you? Okay, it's the sixth element. 4 electrons around it. 4 valence electrons.
It can hold 4 bonds.
Okay, 4 bonds. Periodic table doesn't always tell you 4 bonds. But you're now starting to bring in some interpretation, which is cool. Okay, you're pulling from that knowledge that you had back in Gen Chem, arguably all the way back to Gen Chem 1, because Gen Chem 2, nobody ever uses that. Supposed to get a little bit of a laugh. Maybe it was too soon. Gen Chem 2 will show up again in biochemistry, and it shows up again in o-chem 2. For the most part, we can ignore Gen Chem 2 for o-chem. Okay, o-chem 1 at least. So for those of you who are like, thank God, there you go. Okay? So we're pulling back to all that Gen Chem 1 stuff. Okay, number of electrons. Does it have any protons? Neutrons? Is there a mass? Okay, we've got all of those pieces associated with it. So we could start to look at atomic models. Okay, right? We've got the protons, the neutrons, and the nucleus in the inside, tiny little space. Okay, and we've got all the electrons on the outside, right? Okay, so when I think about these things, I try and think about what they mean. So if I see 6 protons, what do I know? I know carbon. I don't necessarily know 6 electrons because I haven't specified that. Okay? If I wanted to balance those 6 protons, yes, I would need 6 electrons. But just the presence of 6 protons means carbon. Okay? So the number of protons define the element. We could also throw in the neutrons because, hey, why not? We did protons that were in the nucleus. Might as well throw the other particle in. What do the neutrons tell us? The atomic mass. Okay? So that's where we're getting isotopes. Okay? That's what those numbers meant. When we move all the way out to the exterior of this, we get our number of electrons. Okay? And the electrons are, at least from an organic chemist point of view, much more important. Okay? One thing that I would do from Gen Chem is I would use that to determine charge. So that if I had the context of 6 protons, 6 electrons, I now know it's neutral. Okay? So I can use the balance of both of those pieces of information to address charge. But I think electrons are more important than just charge. Okay? Why might I think the electrons are more important than just charge? Or in the grand scheme of things, more important than protons and neutrons?
They're involved in bonding.
Why are they involved in bonding?
They can be shared.
They can be shared. Why can they be shared?
That's the way God made it.
I didn't think that hard.
It wants to be a noble gas.
I think process that one a little bit. Noble gas, nah.
Stable.
Where are the electrons? On the outside. If I bring 2 atoms near each other, what's the first thing that interacts? Okay. The electrons are on the outside of these things, okay, of our atoms. That's the most likely thing to interact between these. Does that make the protons and neutrons irrelevant? No, they are still important. When we're making those bonds, it's the electrons sharing back and forth between the nuclei. So those are still there. But it's those electron clouds overlapping and interacting that drives the primary directions. Okay? To that end, which of those electrons would be the most important? The valence ones. That's why, very conveniently, memorized 4 instead of 6 for carbon. Because we're primarily concerned about those valence electrons. Okay? So a lot of what we're doing in this first unit is thinking about how those electrons can move around both an atom and other atoms. Okay? What are their abilities? Okay? So where do our electrons exist? Because we had core versus valence. We have the individual orbitals, right? Are all orbitals the same? No, we had, what's the first one? Fair answer to that question. It's not where I was going. Quantum numbers? 1 is the specific one. If I wanted to refer to any one of those, quantum number would be N? N, right? N, L. Are you shaking your head because I'm wrong? No, you're just like, I don't remember any of that? That's okay, that's fine. Okay, so we'll just do it. Since clearly we're both a little off on that one, let's just move away from that. Okay, so we're placing our electrons for each of these atoms in progressively higher and higher energies. Okay, as we move up, we add a different orbital type. So we started with an s orbital. When we move up to the second energy, we get a repeat, the s orbital and the p orbital. If we moved up, we'd get s, p, and d. Okay? So each of those things scaffold higher and higher. So when we look at how any atom interacts, we have to consider what orbitals are interacting with each other. Okay? That's a new step for us. Do you think that's an easy step or a hard step? I think it's a hard step. You're adding on a whole bunch of extra directionality, where those individual orbitals are. Okay? Not only where those individual orbitals are, but to know where they are, what would you also potentially need to know? What does it look like? To know where something is, you would have to have a shape. So we'd have to bring in shapes. So we get S's being spheres, P's being dumbbells. If we brought in D's, we get clover leaves. All of those intricate shapes are now being manipulated in 3 dimensions all around these atoms. What makes organic chemistry so beautiful and so difficult is that we are trying to model 3-dimensional things. When you ran a chemical reaction in Gen Chem, did you model a 3-dimensional thing? You're like, no, we just had a line. Reactants plus reactants go to products. Nice and linear. O-chem isn't linear. For those of you being like, but didn't we model 3-dimensional things? You kind of did. You use the mathematics to model it. 152. Arrhenius. Oh, someone started to remember. Okay, when you studied that kinetics, okay, yeah, all that fun stuff, rate laws and all that fun jazz, okay, that was looking at this stuff, but from a numerical method, okay, quantifying it. o-chem, I don't like numbers, and so we tend to avoid and kind of skirt the calculations as much as possible. And say, are there qualitative ways that we can approach this information? Okay? So, it is really complex. So the very first thing that an organic chemist is going to do is take a look at what atoms we're going to study. We already addressed carbon. That's up there. That's convenient. Does anybody notice anything interesting about this periodic table? There's no transition elements. Anything else? Got rid of a whole bunch of stuff at the bottom. Okay? By adding in this having to deal with three-dimensionality and having to deal with orbitals, we've made it so vastly more complicated that what did we decide to do? Ignore most of the elements. Because most of those elements have a whole lot more complicated things going on within it. So we just want to get rid of them. Okay? So in Gen Chem, you were 118. Notice we even deleted the numbers. It's going to be like it's 13. Okay? There's a whole lot less. Right? On top of which, organic chemists have a hard time with those d orbitals. And those d orbitals show up when we move into that third row. Right? So like all of these become kind of tricky to deal with. So we delete those too. Okay? So for those people that are like, I didn't understand it, I'm just going to forget it. Ta-da! Welcome to organic chemistry. Didn't understand the chemistry. Delete. Focus on something else. Okay? We just deleted a lot for you, so you can't delete anymore. Okay? As you move further through o-chem, we'll start to layer some of that back in. And we have to think about how the basics of what we're looking at here, those SPs, and how those would translate into the d orbitals and what effects we're going to start to see out of those. Okay? So other things that we want to pick up. What patterns do we have here? I know, we cut all of that out. So now you're like, there's no patterns. Well, there's still patterns. What's that?
Diatomics.
Okay? We could think about diatomics. Why are there diatomics?
They exist with only two of them together.
They exist as two together. Why? Because it makes them stable. Organic chemistry is about doing what? Reacting things, which by definition means they're not stable, which means don't got to worry about diatomics. Delete. I said you couldn't delete anything. You just did. Good job. What other trends? Electronegativity. Electronegativity is a huge trend. Okay? It is probably one of the most important, if not the most important trend to have nailed in Gen Chem. So that when you get to o-chem, we don't have to have that discussion. So you can tell me the most electronegative element is very clearly the upper left-hand corner.
No, chlorine.
My upper left-hand corner. Fluorine is our most electronegative. Okay, what's the second most? Isn't chlorine just the same distance as oxygen? We run into a little weird gray area there, right? Okay. Have you heard of that phenomenally interesting forced hydrogen bonding? Yeah, why do we have hydrogen bonding? It's due to a difference in electronegativity. When do we have hydrogen bonding? Nitrogen, oxygen, or fluorine. Why? They're the three most electronegative elements. So if you know why hydrogen bonding happens, you now have the top three most electronegative elements. After that, the trends get a little bit wishy-washy, but for the most part, as we trend to the upper right-hand corner, right-hand corner of our modified periodic table, we're most electronegative. What other trends could we get? Electronegativity, I will abbreviate as that Greek letter chi or squiggly x. Okay, I heard something about size. What's our trend with size? What'd you guys memorize? Bottom left is what? I'm going to regret this, but I'm doing it. Okay? That's fantastic. That is true. But remember, we want simple. Okay? And in that simple, when we look left to right, guess what happens to the size? It's a small change. Do electrons have mass? Yeah. Do they contribute to our mass? No. They're so small we can ignore it. Guess what happens with size across the row? It is irrelevant. We only have to worry about size going down a column. Simplify. What other things do we have within our periodic table? Touché. Next. Ionization energy, relevant to electron affinity. The crossbreed of those is actually the important one, which is electronegativity. So we don't need to worry about ionization or electron affinity. Nothing else? You're like, there's nothing else in there. Stop using fancy words I don't know. Metallic trend is the same as electronegativity. For the most part, we don't care about metals because this is organic chemistry. So that was one of the big deletions we did early on. Blue box, purple box? S and P. Okay. I did hear a cations and anions. That's not a bad one to nail down in there. Okay. These are some of those big pieces that we need to nail down and make sure that we're roughly confident on. Why? Because if we spend time trying to think about each of these things when we're trying to do something else, guess what happens? We confuse the whole puzzle and everything falls apart. So if we can try and memorize some of these big trends quickly and early on, we then just have to apply them later on. Make sense? Okay. So we covered the big ones I wanted, which were the orbitals, the size, and the electronegativity. So we'll go ahead and push forward. So I bring two atoms together and I get an interaction. What's the result? We could get a bond. Is that it? Imagine these were people. You brought two people together. Every time you brought them together, poof, married couple. Like chaos. Okay. I'm not sure if that was the two people together or the married part, but you know. What are we going to get in that interaction? Yes, we could get a married couple. What else could we get? We could get a repulsion. We could get them not interacting at all. We could get them interacting and being like, hey, do you just want to study o-chem? Because I don't want to do anything else with you. Okay? Let's just be friends. Let's go see a movie. There's a whole range of interactions that can come out of that. Okay? Chemistry is no different. Okay? That interaction could go any which direction. Okay? What if it's a very strong interaction? What might we call it? Why would you call it a bond? Because bonds are our strongest attraction. What if it's not a very strong attraction? We could call it a force. Okay? Those people wondering, how did those people figure out bond and force so quickly? They had me for Chem 130. Okay? Most of chemistry boils down to bonds and forces. And it's just how we transition between those. Okay? Well, what defines a bond? Anybody want to venture that one? Sharing of electrons. Okay, is an ionic bond a bond? Define ionic bond. Metal to nonmetal is an example because they aren't always bonds. Metals and nonmetals. The transfer of electrons. Is a transfer of electrons the same as a sharing of electrons? No. Ionic bonds straddle a very weird category between being pseudo-sharing and pseudo-not sharing. Ionic bonds are the exact line that differentiates bonds versus forces. Okay? So when you're told to memorize bonds, you have ionic, you have covalent, you have hydrogen bonding is a fun one because not a bond. It's a force. You're like, but it says bond. Stupid name. Don't worry about it. Not a bond. Ionic? I can give you a hint. Covalent is typically what I call it too, but almost always we throw in an extra word in front of it. Non-polar covalent. Typically, the other one would be polar covalent. There are 3 bonds. So when we look at a compound, we want to be able to address those 3 bonds. Why address those 3 bonds? If we know those 3 bonds, we then know what force comes out of them. Why do I care about the force? There's a strong force between 2 atoms. What does that mean about the energy I have to put in to break them away from each other? I have to put in a lot. Is there something that would help me to define or rank an ability for 2 atoms to be pulled away from each other? Like melting points, boiling points, chemical reactivity, solubility. Those are all based off of intermolecular forces. The intermolecular forces are dictated based off of our bonds. Okay? So, we can get bonds or we can get not bonds. Our bonds, we had ionic, polar covalent. Did I double that? I didn't double it. Or non-polar covalent. Okay? As a little preview, our ionic bonds lead to what kind of forces? Okay, that one's a bit challenging, so we'll throw that one out. Non-polar covalent bonds lead to what kind of forces? London dispersion, okay. Is that starting to ring bells now? London dispersion forces, van der Waals, probably my least favorite category. London dispersion, van der Waals. What's the other one? Oh. Temporary dipole. There's a temporary dipole. There's another name for it, I can't remember. Temporary is a wrong word. Okay? What can you tell me about those forces? They're weak. Okay, so we'll pull on it some memory. They're weak forces. Why would they be weak? Where did they come from? Non-polar covalent bonds. What's happening in a non-polar covalent bond? Equal sharing of the electrons. So here's atom A. That's not writing. It's still not writing. That's because I have an eraser selected. Atom A and atom B, both of those have positive charge in their nucleus, right? If they are equally sharing the electrons, where are the electrons? Equally sharing? Our electrons are anywhere on all the way around. Increased in between. Why increased in between? They're sharing those electrons. By equally sharing those electrons, what happens to the charge or the apparent charge at any one location around there? It's neutral. There is no charge. Okay? The whole point of all chemistry is to do what? Achieve neutrality. By being neutral, we become more stable. And for those of you wondering about that and being like, I don't really know that's true. Okay? There is a place that is exceptionally not neutral in this room. And it's not just my brain. Where is that place that is exceptionally not neutral? Say we're very hot right now, getting cooler, ooh, getting warmer, hot again, getting cooler, hot, hot. The electrical outlets, for those of you who have done electricity, it's a hot wire, right? Okay. There's a lot of charge in the wall, in our electrical outlets. That charge is inherently not neutral. If you stuck a fork in it, what happens? The electricity moves out. Why? What is it trying to do? It's trying to neutralize. By doing what? Going through you to the ground. Okay? That's not pleasant. Don't do that. Okay? What if we start neutral? There's no reason for it to interact with anything else. Which means when I bring a second one near it, what do? Nothing. There's no reason to interact. There's not a repulsion. There's not an attraction. There's nothing, which means the attractive force between them is next to nothing. What happens as we move up to a polar covalent bond? Well, now those electrons aren't around both atoms equally. They'd be more around, say, atom A than they were around B. So if I bring a second molecule near B, what is B going to look like? It'll be charged. What charge should B be showing? A positive. There's no electrons around it, which means the only thing left over would be the nucleus, that positive charge. Okay? But the electrons could move over there, so that ends up being a temporary positive. Okay? Induced, that's the word. Induced, not temporary. Sorry. Okay? So what we're seeing is how that charge becomes more apparent. The more apparent it becomes, the more likely it's going to want to interact with something else. Why? It needs to neutralize that charge. Okay? So if we have a polar covalent bond, that ends up leading to a dipole force. Di meaning two, right? We have a positive and a negative. What did I just draw? A dipole. If I bring two of these near each other, what do I have? I have a dipole. That's literally where the name came from. What happens with the ionic one? Becomes an ionic force. Okay? Each of these kind of double off of each other. Okay? What we're going to end with isn't going to be so much this, because where this was supposed to end was just looking at bonding, but then I got excited about forces. Okay? We are officially done, so I'm not asking you to do this right now. But if you got a couple seconds, go ahead and try and figure it out. Lewis structure for the complex ion sulfate. Okay? Teaching has been being homogenized relatively well recently, which means hopefully everybody will give me the exact same structure of sulfate. It's not a guarantee, but that's what I want to see. So when we start class Wednesday, we'll run through questions, what you found in the syllabus. If you've got any questions, like I said, you can always email those to me, and I'll just put them up. Okay? And then we'll look at what the structure is for sulfate, and we will move from there. With that,